Alright, welcome back from MALDI analysis of the analgesic Tylenol. Okay, so what we need to do is make up a sample solution that's going to contain our sample, our standard, and then a little bit of solvent. Okay, so here we have our sample, stock, and this time we're taking 5 microliters. Putting it in an epi. Yes, 5 microliters. So, just so you can see what that looks like. You see that little B curve in there? There you go. That's what it looks like. I got rid of mine. Alright, now we need our standard. We're going to put 5 microliters of our standard. Something's wrong. Oh, that was weird. Oh, wrong tip. That's why. I'm a little bit tired right now. Okay, so we've got 5 microliters of our standard. That's what it looks like. Can you see it in the tip? We're going to put that in there. And then we have 1 microliter of our THF methanol laced with sodium chloride. That's it. That's what 1 microliter looks like. See that little bitty dot in the bottom? That's it. We're going to vortex that. Might have to shake that down to get our drop because we've only got a few drops in the bottom of that now. Alright, and that's what we're going to spot our plate with. Now this is going to have to be LDI because our mass is too low to have a matrix in there, but that's okay. It'll fly with liquid with laser desorption ionization. All right, but what we have here is universal. Probably too much, but that's okay. We have universal indicator, and what I'm going to do is add a milliliter of solvent. The solvent here is going to be a 1-to-1 methanol water. With a 0.1% acetic acid. That should be TFA, I think. Let me see if I have any TFA made up. No, I do not. Let's try this. We're going to try it and see. We have to have, the reason we have to have the acid in here is so that we get a good layer of crystals with our matrix. Since we're not using a matrix for our sample, I'm hoping that this is going to be good enough. Let's mix that. We are going to use this as our calibration standard then. We still have some solid particulate in there. That's good because this is supposed to be a saturated solution. Alright, label everything so we know what's what. This is our matrix, universal, today's date is 3/27/20. This is also in 1-to-1 methanol water. And it's got some acetic acid in there. Alright. Now, this is what a MALDI plate looks like. When you open it up, you can see that you've got little circles in which to place your sample. For MALDI, you never use more than 1 microliter of your sample prep on a spot. So we're going to take our plate and we're going to put a microliter 1 microliter. And we're going to spot this in a couple of spots just because we don't want to have to take it out of the instrument once it's loaded. All right, now to do this is tricky because sample preparation is 85 to 90% of the quality of spectra that you get out of MALDI. All right, so we're going to see if Bobby can get another shot of this way. So what you have to do is you just have to barely put that on there without touching the tip to the MALDI plate. Let's do another spot just in case. There's different techniques that you can use for sample preparation. All right. This is our sample that we had. We're going to take 1 microliter of it, place it on our plate a little bit below using the same technique. I'm going to put it in C. Yeah, this one runs a little bit because it's got some THF in there, so. That one may have dried on the end of my pipette. Oh, that bubble's not good. It's going to cause my crystals to be off. All right. This has to dry before we can put it in the instrument. So let's go talk about the instrument while this is drying. All right. Here we have MALDI. Somebody keeps pushing that down. So we use Flex Control to run the MALDI. We're going to open that up. And this is what the program's going to look like for control. I'm going to select a method here. Okay. No, I don't need that. Not finding my methods here. Here's methods. Here's methods. Where's my USM methods? Okay, so here's my methods. For MALDI, your methods include everything that the instrument needs for parameters to run your samples. Okay, so fast is something you're not going to have to worry about unless you deal a lot with proteins or just proteins or peptides. The L is the first letter in our methods. That stands for linear mode. And the R stands for reflectron. Now, what happens is you have a big tube inside the instrument. While this is drying, we can actually open it up and look. So you have a big tube inside the instrument. So if you look in there, that's the big tube that is filled with a vacuum. Okay? If you look up there, you have detector rings up, and you probably can't see it very well with video because this way up in the dark. Okay. So what happens is Your sample goes in here. It's hit with a laser beam. It excites those molecules. You get a plume of positive ions that then you have a plate then in there that has a voltage on it, and one right above it that toggles with just a slight voltage difference. When that voltage difference is seen or felt by those ions, they start to move, what we call fly. On the other side of that, they see ground. So they're going from like 18,000 volts to ground, like boom. And so what that causes is them to go whoosh. And that's why it's time of flight. It's how they're moving in that vacuum tube. Okay? Now, the smaller molecules move faster, just like a marathon race. The big, heavier molecules are a little more sluggish and they take more time. And that's why the time of flight is used for that. Okay? So, linear mode, your sample starts out here, your ions start here, and they go to the top. Okay? Reflectron mode, they go here, they're stopped, diverted, and they come back down here to another detector. So reflectron is very good. You have more accurate data because you have a longer time of flight. It's almost double time, so you get better separation, you get better quality spectra. But there are limitations to it. So you can only do about 15,000 mass units before you can no longer use reflectron, and you have to use linear. Okay? You have to use linear at that point. All that in there are the high voltages and the electronics. So that's inside our instruments. Alright. This is dried. You see we no longer have any liquid on our plate. It's all solid, you see on there? Okay, so now what we're going to do, let me back up. So this is the linear mode, this is reflectron mode. The second letter you see is either N or P. N for negative mode, P for positive mode. This instrument, you have to load that ion polarization with the method. You cannot click a button and change the polarization like you can with the LXQ. Okay. So we're gonna use, let's just go with pet mix for our method. And now what we're gonna do is hit this little button that's going to allow us to load our sample plate. This is the camera inside that's watching the docking station move. It clicked. I can now open. This is what it looks like inside. It's keyed, so our plate can only go in one way. And then we're going to close it. And we're going to dock our plate inside the instrument. I feel like there should be elevator music playing now, huh?
You can add that in post. You be able to point with your finger on the computer what you're going to push and stuff.
Okay.
Makes it a little bit easier so I can zoom in and.
Alright. So you can see that our plate is now pulled inside the instrument. This is an actual rim of one of those circles that you saw on the plate. What we're going to do now is we're going to go to status, details, and we're going to look at our vacuum. Our vacuum is already passed, so we should be good. I just clicked on details again. So now what I'm going to do is go to detection. This is set for 820 to 3560, which means that somebody changed my method and they should not have. So what we're going to do is we're going to pull this down because we want to detect lower. Let's go to 220. We're going to use the same range that we used on, let's just go to 820 just for fun. Okay, that's the range that we're detecting in. Alright, the spectrometer now, we have deflection on, and this tells me that everything below 800 mass units is being deflected. It's not going to detect it. We don't want that because ours is 177 with sodium in there. So we want to see those masses. So what we're going to do is we're going to turn that off. We're going to click this off, and so it's going to detect everything. Alright? Alright. Now, what we're going to do is we're going to click up in here. I'm going to put my mouse where I want my crosshairs to go to. Actually, let's start here. My sample, the first calibration sample is in A1, so I'm going to click A1. Look how off that is. I'm going to have to do some work on this. So this is A1, and that's our crystals on A1. I've got some big lumps in here, so I didn't do a very good job with this sample. But let's come in here, and let's start shooting this. So this is allowing me to fire my laser, and I'm clicking add here for my sum buffer. This is going to add my spectra to a sum buffer to increase my peak size. Notice here the intensity of my peak is 3000. That's my highest peak. I need it to be 10 to the 4th to be able to calibrate my instrument. So I'm going to have to shoot some shots until I get 10 to the 4th. That one's 6,000. Oh, that one's not good. I'm not going to add that one. I'm going to go add that one. Okay, let's go to our sum. So this is your single spectra. This is a sum. So we're going to put on the sum, take off the single, and notice we have now 10 to the 4th. All right, so we're going to go to calibration. I am going to use my matrices. I know I have alpha cyano in there, so I'm going to pick that. So what I do is I go to the left and below that max peak, and the computer automatically picks the peak max to assign for that mass. So now I have two masses here. I can't do quadratic unless I have more. Let's see if I've got another one. Oh, that's not looking good. Let's just use linear mode, because linear will allow me to use 2 points. Okay, so it changed my masses to fit my calibration standard. All right. Let's go back to our spectra. Now let's look at one of our samples. Ooh, I put it in C, right?
Yeah.
I don't see anything. I pulled the energy, the percentage of that laser that's hitting the sample, I pulled it up. is, but it's pretty big. This should be, what is that?
What's the mass of it?
Nothing dimerizes, does it?
No, it shouldn't.
268. That's 211. It's 211. Let's try another spot. I don't see any crystals. It's that same one showing up. Alright, let's save as. Oh, it's just a single. Let's see, this is oh no, I don't need this under training. I need this under this one. Why did it do that? There we go. Make sure that your pathway is right for your file to save. This is acetaminophen plus a spike. Oh, I forgot to put that was positive mode. Okay. So let's go to negative. Oh, it's outside our range. Reflection is off. Detection is not low enough. I didn't get anything pulling out of the baseline, so I'm pulling my laser percentage up, pulling my energy up. Still not getting much out of the baseline. Huh. We got something. lots of something. My baseline's not degraded, so it looks good. If you have too much power, your baseline will look degraded and it'll look kind of noisy and thick, and then it'll go down. So this is a little bit degraded because of the power, but not so much that we're losing spectral data. We got a bunch of stuff in here though. I don't know what it is. Let's try a different spot. It looks like, oh, okay, so what I just did, sometimes when you get too close to 0, there's an electronic spike in here. So I pulled off my mask just off of 0, and when I did that, it looks like these peaks got real big. But in fact, if you look at the scale, they didn't get big. This is still pretty low peaks and some noise. So it's not, you have to pay attention to what that scale's doing. That's nothing. That's at 300. That's something. We're going to add that. Nothing. That's something. We're going to add that. Okay, so now let's save as. Negative mode. Negative. Alright. The good thing about the MALDI is the cleanup, because now all I have to do is pull my plate out, spray off the plate with whatever solvent that analyte's soluble in, let it dry, and put it away. That's it. It's pretty nice. The cleanup is anyway. Now what we're going to do, cancel that. We're going to minimize. We're going to go to Flex Analysis. Contact Looper. I'm going to open up my file. So here I'm going to browse. Class, acetaminophen plus spike, okay. So if I click on that and open, it gives me the spectral data that we had for that. Now, from before, positive mode should have a sodium on there, so it was 170 something. We don't see a lot in the 170. What's this? Huh, that's interesting. This has a mass unit difference of, what, about 6? Which tells me this might be dimerizing. So if I've got 2 dimers of the deuterated, 2 compounds of the deuterated sticking together, and 2 of the regular sticking together, that would put me at, no, that would put me at not enough. No, it's not a dimer. I don't know what that is. Let's come back in here and look to see if we can find anything in this range. So we have nothing. What's our regular one? This is just noise. I don't have anything. There's really nothing for me to print out for this. So, let's look at our next one. The negative ion mode. Let's take off our positive ion mode. This is our negative. Now we have some stuff in here. Let's pick these peaks. What's it doing? Okay, so MALDI, if there's not enough room on the page, it'll just add it to your mass list here. Let's open this up so we can see what it's doing. Negative should be what? Negative ion mode?
Should be 153 for the deuterated.
We've got something here. Huh.
That's him. Yeah, those are the 2 peaks we're looking for.
Okay, so let me print this out. This one has the area. Why is it paused? So I will try to print this out, and then I'm just going to spray or take regular methanol and spray my plate down and put it back in the holder, and that'll be it. See you next time. Bye. Stay safe.